Okay, let's go through chapter 14 of chemistry, thermodynamics. I'm just going to go through and then I will post you pictures of my notes, I think. Maybe. Some of them are more legible than others. Okay, enthalpy is a measure of a chemical system's potential energy. Remember we talked about how chemical, what are they called? Chemical molecules have the bonds. There we go. The bonds have potential energy. And if we break those bonds, it can turn into kinetic energy that can be used to do work. Enthalpy, we use the letter H for its symbol. We cannot measure enthalpy directly, but we can measure the change. So how much does it change? But we don't measure it directly. So exothermic, our change in H is going to be negative, and endothermic, the change in H is going to be positive. You girls. Okay, enthalpy change and bond energies. Where is the potential energy in chemistry? It's in the chemical bonds. We have a chemical reaction takes place to break the bonds, which makes it unstable. And then we release energy when new bonds are formed because it becomes stable. So we have a chemical bond. When we break that chemical bond, it's now unstable. So enthalpy, also you can kind of consider it a measure of like chaos if you want. That's kind of a way to think about it. So when you break the bonds, we're going to take energy to break those bonds, which creates more chaos because now things aren't bonded and they're not happy. They don't have full valence electrons, so they're not happy. When they rebond, they can release energy. They're now stable. They're able to have full valences. They are happy. Okay, the change in energy. You take the energy to break the bonds minus the energy to form the bonds. Energy to break the bonds minus the energy to form the bonds. And that is in your book, hold on page 420. Okay, bond energy. Bond energy is the energy required to break a mole of a given type of bond. And you have in there a chart of bond energies. And on your test, you will have a chart with bond energies and some other things. But bond energies are on there. You are not expected to memorize bond energies. Then it goes through example 14.1. I'm not going to go through it because it's right there in your book for you. But you can see how you use the coefficients, those big numbers in our chemical equations. The big numbers are our coefficients, and we use those coefficients multiplied by the bond energy from the chart, and we put in the breaking side, so the reactant side minus the product side, and we'll get our change in H. Hey, Ruby. Not right now. You can play on the tablet. Okay, yes, you can. Come here. If you need me to turn it on. Okay. Okay. Ruby needed to ask me a question. But she's the cutest. Okay, what else? Okay, so we use our chart to find them. If you look at page 425, it gives you equation 14.2, and it tells you the change of H is C. So it gives you an equation. Okay. It talks about state functions. Okay, let's do that one. State function is a property that is independent of the path. And the book gives you this example of like a winding road. And if you calculated how many miles it took you to drive this winding road or to walk straight down the path, it would obviously take fewer miles to walk straight down the path than to go the winding road. That is not a state function. But if you looked at the sea level of where you started and where you ended up, that would be a state function because it doesn't matter how you got from A to B, point A to point B, you're still there. So that is a state function, things that are independent of the path you take. So enthalpy is one of those things. It does not matter. We do not have to figure out how do these bonds break and which bonds break and which bonds form or any of those things. It is a state function. It does not matter the path that it takes to have that done. So we use the chart to find the change in H. Also, yeah. Oh, okay. So the chart on page 420 gives you your bond energies, so you can determine the change of H. And then the chart on page 424 gives you the enthalpies of formation. So those are the change in H's. The change of H of any element in its natural state is 0. So if you just have O2, for instance, it's 0. And then equation 14.2 is a good one to have. So it shows you that, it gives you kind of a formula there. The little a, the little b, the lowercase letters, those represent the coefficients. The uppercase letters represent the chemical formulas. So it shows you that you can take the coefficient of C times the change of F for C that you would get from the chart, plus the change in the coefficient of D times the change in F of D from the chart, and then minus the A ones. Okay. So, and then 14.2 takes you through an example of that. This makes me want to check something I said. Hold on. Okay. No, I'm good. Okay. So go through, kind of process through 14.2 just so you have some ideas. Enthalpy and stoichiometry. I know you all missed stoichiometry. So, in stoichiometry, remember we have grams, and we can go from grams to moles using the periodic table. So, in this example, you would be able to find moles using the periodic table AMUs. So, if you're given 150 grams, you can use the periodic table, divide by the AMUs on the periodic table for that, and find the number of moles. Elizabeth, can you let Boomer in, please? And then compare that with the moles from the equation and change of F to find the total. So then you would want to do your ratio. So do your factor label method. Follow through 14.3. See how they do it. Use the factor label method when you're doing that. Make sure you include whether you're doing grams or moles and which element or compound you are using. Activation energy. It's the energy required to initiate a chemical reaction. So we are sitting here all the time, and we have all kinds of chemicals in the air around us, but we don't have things just suddenly catch on fire or chemical reactions just suddenly occurring. So the activation energy is the amount of energy to kind of kickstart it, to get it moving. Trying to read what I have here. The product potential energy has to be greater than the reactant's potential energy. Okay. So, and they give you a little picture on page 428 that shows you have reactants and products and the change in activation energy and the change in F. The one on page 428 is for an exothermic reaction. In an endothermic reaction, the products will end higher than the reactants. So this is exothermic. Endothermic, the products will be higher than the reactants. If you look at the picture on page 429 for example 14.4, that is an endothermic reaction. And you do need to be able to tell when you look at a graph, is it endothermic or exothermic? That first big hump, though, is the activation energy. So the smaller the hump, the less energy needed to get a reaction started. Thermodynamics, the study of relationships and conversions between different forms of energy. And we have some laws that govern it. The first law, energy cannot be created nor destroyed. It can only change form. So I cannot make energy. You cannot make energy. It just changes forms. Entropy is a measure. So this is entropy. Oh, I'm sorry. I said earlier that entropy could be the chaos. I think entropy is the chaos. Enthalpy is not. Sorry, said that wrong. Entropy is the measure of the amount of energy in a system that is not available to do work. So it's too disorganized. You have like random bits of energy floating around and they're just too disorganized to actually do work. That is what entropy is. We use the letter S for it. The second law of thermodynamics says that entropy of the universe can never go down. It either stays the same or it goes up. So another way of saying this is that everything's moving towards chaos. Nothing moves towards less chaos. Actually, if you think about it in terms of evolution and why evolution isn't true, this is a great example, because this would be, again, things getting more organized and more complex would be against the second law of thermodynamics. Things can go more chaotic or they can stay the same, but nothing gets less chaotic on its own. So changes in entropy. The change in system plus the change in surroundings has to be greater than or equal to 0. So when you're looking at these, some rules. The solid phase is the lowest entropy phase, while gas is the highest. Solid is the lowest entropy phase. Gas is the highest. Obviously, liquid is in between. The larger the number of molecules, again, that coefficient number, the greater the entropy. And again, it gives you an AA plus BB goes to CC plus DD, and how you can use that. Their absolute entropy chart is on page 437. So that allows you to get the number for the entropy. You can use that chart. So when you're like, how am I going to figure this out? You're going to use that chart. When you are trying to figure out the sign, when it says to figure out the sign, what they really want is greater than or less than type sign. A greater than, equal to, or less than, equal to sign. If you don't remember that, remember the big mouth has to chomp at the big number. The arrow points at the little one because it wants to point left. I learned it both ways, so whichever way helps you remember greater than, less than sign. So you need to figure out when it asks for that, that's what it's asking. So in comprehension check for number 10, it's asking you, is it greater than, equal to, or less than, equal to? And so you're going to look at the states of matter, is it a gas, solid, or liquid, and then the number of molecules second. First, you look at the states, and second, you look at the number of molecules. So then we have 14.6 goes through an example of determining the change in S, and it is very, very similar to determining the change in H, so you can follow through those. These are not super difficult because they're very similar concepts. And then we have Gibbs's free energy, which we represent with a G. When the change in G is negative, the reaction is spontaneous. When the change in G is positive, the reaction is not spontaneous. Hold on, let me see. Is the next chapter? Yeah, the next chapter is kinetics, which allows us to figure out what causes reactions to go at speeds. Like kinetics is the speed of the reaction, so that's why we're doing this first. Like what causes reactions to go, and I'm assuming we will get into catalyst, which are things you can use to kickstart a reaction. Change in G for any element in its natural phase, again, is 0. The change in G, it gives you this very similar equation, and there is, again, a chart for Gibbs free energy. Where is that at? On page 444. So there's a chart for that, and you follow through. These equations are very similar, just using different charts. So make sure you know which chart you would use on your test. All 3 charts will be together. If you have any questions, let me know, and I can work through individual problems, because you guys are going to work on the review problems this week. So make sure you understand how to do those. And make sure to go back and check your chapter 13 extra practice problems. It's on you to check those and make sure you're understanding what you do. So, okay, that is the basics of chapter 14. We're talking about the change in enthalpy and the change in entropy. Entropy is the chaos. Enthalpy is the potential energy. So enthalpy is the potential energy. Well, really, the change in potential energy of your system. Entropy is the measure of chaos in a system. And those relate to whether reactions are going to actually occur or not occur, or whether they need a kickstart or how much energy they need for them to get started. So there you go. Let me know if you have any questions.